Alright guys, so I want to take a quick look at a interesting problem. It is a function, and we're going to take its derivative and maybe show you a few different ways to go about taking the derivative and then simplifying the derivative. So the derivative, or excuse me, the function is f of x equals x over square root of x squared plus 1. Okay. If I remember correctly, I think this is number 27 in section 3.4, I think. I could be wrong though. So 3.4 is the section about the chain rule. So notice this is going to use the chain rule because you must use the chain rule pretty much anytime you have the composition of two functions. And notice here on the bottom we do have a composition of two functions. We have the composition of the square root of x and the square root of x plus 1. So just as a short aside here, square root of x plus 1, x squared plus 1, equals let's say f composed with g of x, where f of x equals the square root of x and g of x equals x squared plus 1. So, you know what, yeah, that's right, okay, sorry, I thought I made a mistake. We're good, okay? So that is a composition which is going to require the chain rule. Now, let's take a look at this. Probably the way most of you guys would do this when you see it the first time would be to use the quotient rule, because clearly this is a quotient of two functions. However, there is another way to look at this. You could say, just by rewriting this according to the rules of exponents, you could say this is equal to x times, let me back up just a little bit. I just reworked some of the controls on my tablet here. Let's see, so this would, you could rewrite this as x divided by x squared plus 1, first of all, to the 1/2 power. The square root in radical notation is equal to the 1/2 power in exponential notation. But then we could say this is equal to x times x squared plus 1 to the negative 1/2 power. So as you notice here, we could actually use the quotient rule in this situation, or we could use the product rule in this situation. Now, is one easier? Maybe, maybe not. That's up for you to decide. But you can get the exact same answer using different techniques. So let's do the quotient rule first. Okay. So what does the quotient rule say? Quotient rule says that f prime of x is going to be equal to a really big fraction. So just make a really big fraction bar, and what does it say? It says you take the derivative of the top function, so we'll say the derivative of the top function, which is just x, times the bottom function, which is the square root. You know what? In this case, I want to, I'm going to just refer to the square root of x plus 1, x squared plus 1 that is. I'm going to refer to that as x plus 1 to the 1/2 power, just to make things, easier when we're working with this derivative. So I'm going to refer to not radical notation, but I'm going to refer to the exponential notation, just like this intermediate step here. So it's the derivative of the top function times the bottom function, which is x squared plus 1 to the 1/2 power. Okay, then what else does the quotient rule say? It says subtract off the derivative of the bottom function, which is x squared plus 1 to the 1/2 power, times the top function, which is just a plain old x. Then we divide by the denominator squared. So that is x squared plus 1 to the 1/2 power squared. Okay. Now we have to go ahead and figure out that derivative and that derivative and then start the simplification process. So let's see here. We can say this equals, we still have a big fraction. Well, what's the derivative of x? The derivative of x is just 1. So this first term on the top left-hand side just simplifies to x squared plus 1 to the 1/2 power. Now, here's where things get a little tricky, because this is where the chain rule comes in. This is where that composition is. So remember, to take the derivative of a composite function, the chain rule says you take the derivative of the outside function. The outside function is this guy right here, the square root of x. And this is the inside function. So we take the derivative of the outside function. So think about the square root of x as x to the 1/2 power. So we have minus, now the derivative of x to the 1/2 power, let's just go ahead and write this, x to the 1/2 power. The derivative of that is 1/2 times something to the 1/2 minus 1 power, which is negative 1/2. Now I need to make those a little bit bigger. To the negative 1/2 power. Now, it's the derivative of the outside function evaluated at the inside function. So the inside function goes right here, x squared plus 1. Let's make that a little better. But then you have to multiply by the derivative of the inside function. Inside function is x squared plus 1, so the derivative of the inside function is 2x. But then, okay, this entire thing is the derivative right here. Don't forget about that other x we had hanging out over there. I do that a fair amount myself. I'll do the chain rule that's inside the quotient rule, but then I'll forget to multiply by that other term we had over there on the far right hand side. Okay, so that's the numerator, all the derivatives. Now what about the denominator? Let's go ahead and simplify that. According to the rules of exponents, we have an exponential expression raised to another exponent. So what do you do in that case? For instance, just off to the side, if you have x to the a to the b power, you can rewrite that as x to the a times b. Okay, so you multiply the exponents when you have an exponential expression raised to another power. So we have a 1/2 power raised to a second power, so you can multiply those two exponents. 1/2 times 2 is 1. So in the denominator, we just simply get x squared plus 1 to the first power, otherwise known as just x squared plus 1. Now, this is the derivative. Okay. In some cases, there are some folks who would not care if you stopped here, because that's the derivative. However, it's generally accepted that you need to simplify this as much as possible. Now, what do we mean by simplify? We mean usually if there's multiple terms involved, well, if there's multiple fractions, reduce the situation to as few terms as possible and eliminate negative exponents. So notice we do have one single fraction. That's good. That's a start. But we do have negative exponents. And we can do some combining here on the numerator. So we want to make this as few terms as possible on the numerator. Okay? Now, it may not be obvious here what to do. You may say, want to rewrite this in terms of radical notation, which will produce a fraction here because you have a negative 1/2 power. You might think you might prefer to think of it that way, then get a common denominator to simplify the numerator. But here's how I would do it. Now, you have to remember your rules of exponents here. So the denominator is just going to chill out for a minute. X squared plus 1. Okay. Now think about this. If we're trying to eliminate negative exponents, we have a couple things we can do here. Like I said, we could rewrite this in terms of radical notation and then combine via common denominator. But there's one way to do it would be to factor the numerator. Okay. Now we can factor the numerator because we have an x squared plus 1 term right here and an x squared plus 1 term right here. They're raised to different powers, of course, but you can still factor this, and it's kind of weird how it works. Now the question is, what would you want to factor out? Okay, x squared plus 1 raised to what power would you want to factor out? Well, I guess you kind of have two options. You could either factor out x squared plus 1 to the 1/2 power, or you could factor out x squared plus 1 to the negative 1/2 power. Either way will eventually get you the right answer. I'll just kind of tell you right now, factoring out the negative 1/2 power probably goes a little faster because you can get rid of the negative exponents faster. So let's just for the sake of argument, let's say we factor out a negative 1/2 x squared plus 1 to the negative 1/2 power. So over here I'm going to say x squared plus 1 raised to the negative 1/2 power. Now, what would that leave over inside my parentheses? Now, let's think about this. What it leaves over is what I would need in there if I was going to distribute such that I get this original thing back. Okay? Do note, real fast, that in this upper right-hand side, we have a coefficient of negative 1/2 and a 2 right here. Negative 1/2 times 2 is just going to leave us with a negative 1 coefficient, and x times x is x squared. So I guess there's one small step of simplification. I'm just going to do it in my head because it's not really worth it to leave a line to it right here. So this top right-hand term actually simplifies to negative x squared plus 1 to the negative 1/2 power times x squared. So the question is, okay, if I factor out an x squared plus 1 to the negative 1/2 power, what's left over here in the top right? Well, I factored out most of it. All that's left over is the x squared. Well, sorry, negative x squared. And so now the tricky part is, what if we factor out a negative 1/2 power out of this first term, what's left over? Okay, well, think about this. If we were going to distribute, we would need to put something right here such that when we distributed, this is what we got. Now, what does it mean to multiply exponential expressions? Well, with exponential expressions, if you have, say, x to the a times x to the b, that's also can be rewritten as x to the a plus b. So you add, when you have an exponential expressions of the same base, you simply combine right as a single base and you add the exponents. Okay? So I need to put in that blank, I need to write x squared plus 1 raised to some power such that if I was going to multiply this term by this term, I would add the exponents together and get a positive 1/2. Well, what do you think it is? Negative 1/2 plus what equals positive 1/2? Well, I think that's a positive 1. If you put a positive 1 power there, 1 plus negative 1/2 gives you positive 1/2. Now, why is that super useful? Well, you can see in the next step. Okay, think about this. If that is raised to the first power technically, and this is raised to the negative 1/2, what does the rule, or what do the rules of exponents tell you we can do about simplifying this term and this term? So we have, it's like having an x to the 1/2 power. Just think about, it's an x squared plus 1. Just think about a variable to the negative 1/2 power and a variable to the first power. Well, the quotient rule of exponents says you can simply take the upper one minus this minus the bottom exponent. So you get x squared plus 1. Let's see. So you have a negative 1/2 power. You have negative 1/2 minus 1, which would be the negative 3/2 power. Okay. So if you have, we would have x squared plus 1 to the negative 3/2 power, because you would simply subtract 1 from negative 1/2. Negative 1/2 minus 1 gives you negative 3/2. So what is the negative 3/2 power? Well, if you have the negative 3/2 power on the numerator, that actually kicks it down to the denominator. So we're going to have an x squared plus 1 to the 3/2 power down here. And that takes care of those two terms. The only thing left over on the numerator now are these terms, is this set of parentheses. But what's in that set of parentheses? It's x squared minus 1 minus x squared. And so we have negative 1. Oh, sorry. What did I do? I almost did all this work and then made that mistake. It's not x squared minus 1, it's x squared plus 1. Okay, so that is simply, let's see, that is simply a positive 1 left over on the numerator, and x squared plus 1 to the 3/2 power on the denominator. Now, if you really wanted to, you could say this. You could say that's equal to 1 over the square root of x squared plus 1 cubed. But that step right there is not necessary if you wanted to. So these are exactly equivalent, and we have simplified as much as possible. Now, let's say if you went back to this step, but instead factored out a positive 1/2. How might that change things? Well, let's just, let's play around with it and see. So if instead, let's say we factored out a positive 1/2 power on the numerator. So we're still leaving the denominator as x squared plus 1, but we do the other thing and factor out x squared plus 1 to the positive 1/2 power. Now, what would get left over in the parentheses? Well, if we factor out x squared plus 1 to the 1/2 power, we're just left with a 1 there, because we factored out the entire factor. Okay, now what would be left over here? Well, we need to figure out, or first of all, there's an x squared. Don't forget about that. Remember, there's an x squared there. So let's just go ahead and, actually, it's negative x squared. Okay, because remember the negative 1/2 and the 2 resulted in a negative 1. X times x is x squared. Now the question is, x squared plus 1 raised to what power? Now, we need to think about the power here as if we were going to distribute. Like if we were going to distribute this to get this original numerator back, what power would need to go there? Well, I have a 1/2 power here. I would need a negative 1/2 power to get there eventually. So the question is, if we added 1/2 plus what would give us negative 1/2 power? Okay, 1/2 plus what power would give us negative 1/2? And I think it's negative 1, right? Because 1/2 minus 1 would give us the negative 1/2 power we needed. Okay, now what would we have if we had done this? I think it'll take more time than the original way I worked it, but let's see what happens. Okay. Let's see here. So we could do some canceling out here, right? Because this would be, we would have, again, the first power down here, and you have a 1/2 power up here. So we have, you would have 1/2 minus 1 would give us an x squared plus 1 to the negative 1/2 on the numerator, but that would just give us an x squared plus 1 to the positive 1/2 power on the denominator. Okay, so that's just your rules of exponents. Again, the quotient rule of exponents. So then we would be left with 1 minus x squared times x squared plus 1 to the negative 1 power. Okay, so you see there, this kind of is more difficult to work with. I guess what we would have to do at this point is to put this in a complex fraction form. What I mean is rewrite this as what this term means in fraction form. So the -1 exponent creates a fraction on the existing numerator. So we still have the x squared plus 1 to the 1/2 power. Then we're going to have 1 minus x squared over x squared plus 1, because the -1 power kicks this to the denominator. So now we have a complex fraction to work with. This is why I said it was probably easier to do my original way. Okay, so now I need to get a common denominator on this whole numerator. So I have x squared plus 1 still hanging out down here to the 1/2 power. Now what's the common denominator? Well, I can just write this. I have 1 here. My common denominator is x squared plus 1. So I need to multiply 1 times x squared plus 1 over x squared plus 1. So that's x squared plus 1 over x squared plus 1. That's just a fancy version of the number 1. Minus x squared over x squared plus 1. Now I have a common denominator. I can combine. And so I have x squared plus 1 minus x squared over x squared plus 1 over x squared plus 1 to the 1/2 power. Okay, we're getting close here. Now this top fraction still has an x squared plus 1 on the bottom, and then we have x squared minus x squared plus 1, so just this. Then we have x squared plus 1 to the 1/2 power still hanging out down there. Okay, well, I still have a complex fraction. You never want to leave a complex fraction as is. You want a single fraction bar. Okay, so how do you deal with that last step, or almost last step? What you do is you take this top fraction and multiply by the reciprocal of the bottom fraction. That's how you deal with fraction multiplication. You flip this and multiply. So we have 1 over x squared plus 1 times 1 over x squared plus 1 to the 1/2 power. Now how do you deal with multiplying fractions? Well, you just multiply numerators, multiply denominators. So this is equal to 1 over x squared plus 1. Oh, that's a little messy. Let's back up. Plus 1 times x squared plus 1 to the 1/2 power. And then what do you do with exponents when you have same base, same base? This is technically a first power. That's a 1/2 power. You can rewrite this as 1 over x squared plus 1 to the 3/2 power. Notice the exact same answer we got way up here. Same answer. 1 over x squared plus 1 to the 3/2 power. Do note that, the purple version took substantially more steps than the kind of goldish, orangish version. So, if you had factored this way, you would have gotten the right answer eventually, but it just would have taken you a lot more steps. Now, another way, as I mentioned, you could solve this according to the product rule, because now I have this written as the product of two functions rather than the quotient of two functions. Let's see if the product rule turns out to be any easier. Okay, let's see. I don't know. It might be. Let's see what happens. So we could say that f prime of x. Okay, well let's rewrite f of x. Sorry, so I can have it all on one screen. F of x, we said in green, as a product is equal to x times x squared plus 1 to the negative 1/2 power. Okay? So what does the product rule say? The product rule says you take the derivative of your first function. So we have two functions. We have first function and we have second function. Okay? So the product rule says you take the derivative of your first function, so we'll label that as derivative of x. By the way, it is very useful to write this as I am. Like, don't try to do this first step in your head. I probably could most of the time and get everything right, but you're new to this and you need to do most of these steps on paper. Because it's really easy to get mixed up in these complex calculations. So just write out these steps just like I'm doing here. Okay? So we have the derivative of the first function times the second function. So times x squared plus 1 to the negative 1/2 power. So that's the derivative of the first times the second, plus the derivative with respect to x of the second function, which is x squared plus 1 to the negative 1/2 power times the first function, which is just x. So here is what the direct application of the product rule. Now let's find those derivatives. Well, the first one's quite easy. The derivative of x is just 1. So this first term simplifies to x squared plus 1 to the 1/2 power. Okay? Now the second one is the more tricky one. Now we've already done this derivative. It's not so bad. But we have plus, okay, it's the chain rule now. So remember we have the outside function as x to the negative 1/2 power. So we have minus, we're taking the original power out in front. We then have evaluated at the inside function. Then we reduce this power by 1. So 1/2, oh, actually, no, this is a little different than what we did before. Slightly different because we have a negative 1/2 exponent here now. So we bring the original one out front, and then we have times the original exponent times the inside function raised to the 1/2 minus 1 power. 1/2 minus 1 is negative 3 halves. Just get that in your head. You'll see that all the time. Okay? So it's the derivative of the outside function evaluated at the inside function times the derivative of the inside function. The derivative of x squared plus 1 is just 2x. But don't forget about that x we had originally, the first function. Okay, now let's see what this does. So let's just clean this up slightly. Oh, you know what? I made a typo there. From one line to the next. Derivative of x is 1 times this. I left off that negative 1/2 power. I left off a negative sign. So that's good that I saw that instead of wasting much time. So let's clean this up slightly. That's x squared plus 1 to the negative 1/2 power. Now, just like before, we have a negative 1/2 and a 2. So that simplifies to just a negative sign out front. Then we have x squared plus 1 to the negative 3/2 power times x squared. Now, at this point, well, first of all, this is the derivative. In fact, that is the derivative. Okay? Is it simplified? No. Think about it this way. If you were working a problem on a test and you got your final solution and this was your final solution, pretty much most teachers, most textbooks would say that's not a proper final solution, because most textbooks, most teachers say you need to have this completely simplified, which completely simplified, one thing that means is no radicals on denominators. So you would say this actually equals square root 2 over 2 when you rationalize the denominator. Now, are those two numbers the exact same thing? Yes. They're just in different forms. One's simplified, one's not. Okay? So if you got to this part, I would give you a significant amount of credit, because you have gotten a decent way through the problem. The derivative is correct. However, it's not in its proper final form. Okay? So you certainly need to practice your algebra so you can earn all credit and all points. But if you can do the calculus like so that we've done so far, you will get somewhere between half and maybe 3/4 of the credits, since this is the derivative. Now, at this point, what can we do? Well, we can do the same thing we did before by factoring. That is, let's see, if you factor out a -3/2, you would get the answer in pretty much the exact same way that I factored when we did the quotient rule. But let's just say to see something different, let's say what you did was, since one thing we want to do is get rid of negative exponents, let's just say we got rid of our negative exponents first. So we would write this first term as 1 over x squared plus 1 to the positive 1/2 power. A negative exponent kicks the term to the denominator, and then you make the exponent positive. Minus, okay, we have an x squared on top over here, divided by x squared plus 1 to the positive 3/2 power. Okay? So now let's concentrate on getting a single term, a single fraction. Now remember, simplification, you want as few terms as possible and no negative exponents. Well, we've gotten rid of negative exponents, we're good there, but we don't have as few terms as possible. We can combine these two fractions. Now we need a common denominator, so what might the common denominator be? Well, x squared plus 1 to the 3/2 power looks like a good candidate to me, because how can I get an x squared plus 1 to the 3/2 power on this left-hand fraction? Well, I can multiply it by x squared plus 1 to the first power over x squared plus 1 to the first power. Why does that work? Well, remember, when you multiply exponential expressions with the same base, you simply add the exponents. So it's 1 plus 1/2, it's 3/2. So now you'll see I get x squared plus 1 for this left-hand fraction, x squared plus 1 divided by x squared plus 1 to the 3/2 power minus x squared divided by x squared plus 1 to the 3/2 power. I now have a common denominator. Now let's just go ahead and simplify the numerator. The numerator is going to have x squared plus 1 minus x squared, which simplifies to 1 over our common denominator, which is x squared plus 1 to the 3/2 power. Notice again, exact same answer. So this is the case with many of these derivatives. You can do this way, that way, a third way. You just have to make sure that you're employing proper calculus techniques, but there's usually more than one way to approach a problem, especially when you have quotients. You almost always can do something like this and use the product rule instead of the quotient rule, or vice versa, but most people would never go from, most people would prefer the product rule, so you would probably never go from this form to that form, because the quotient rule is more to worry about. But you could, if you really wanted to. You could take a product to a quotient if you wanted to. So, lots of ways to solve these. Just make sure you practice, practice, practice. That's the key in calculus. Practice, practice, practice. All right, if you have any more questions, feel free to ask. More than happy to make tutorials for you, or if they're answer questions on Blackboard, that kind of stuff.